this class, we're going to use calculus to understand the behavior of a family of functions, and we'll be able to find a member of a family given some specified properties. Okay, so a formula such as f of x equals ax squared plus bx plus c describes a family of functions. Okay, so all the functions that look like that, where you put in numbers for a, b, and c, that's a whole family of functions, and we call a, b, and c parameters. So this family is a 3-parameter family because there's 3 parameters. All right, so we want to find a parabola of the form ax squared plus bx plus c that passes through the point 1, 4, and whose tangent lines at x equals -1 and x equals 5 have slopes 6 and -2. All right, so it passes through the point 1, 4. So that means that f of 1, if I put a 1 in for x, I would get a plus b plus c, right? And that should give me 4, because 1, 4 is on the graph. So f of 1 should be 4. All right, and then slopes of tangent lines, how are those measured? The derivative, thank you. So I need to take the derivative of f of x, so I'll write down f prime of x here. It is 2ax plus b. And what should f prime of -1 be? Well, first we can plug into this formula for the derivative, put in a -1 for x, and we get -2a plus b. And what should that value be? What should the derivative at -1 be? It should be 6, because we know the tangent line at -1 has a slope of 6. So that should equal 6. And then I also have f prime of 5, right? The tangent line at 5 has a slope of -2. So I got to plug a 5 into f prime of x, and I would get 10a plus b. And that should give me -2, the slope of the tangent line at 5. All right, so what I have is I have 3 equations, 1, 2, and 3. And how many unknowns do I have? 3, a, b, and c. Yeah. So 3 equations, 3 unknowns, I should be able to solve this. This is just an algebra problem. Okay, so I used some calculus to come up with the equations. Solving the equations is just algebra. So any ideas? What do you want to do to solve these? Sure, we could do substitution. What do you want to solve for? I want to solve for b. It's a little bit easier because the coefficient on b is 1, so I'm not going to introduce any fractions when I'm solving. If I solved for a, I would have had to introduce a 1/2. It's fine either way, personal preference. Okay, so this guy, if I solve for b, I get 6 plus 2a. Just move 2a to the other side. And then I can substitute into this equation, instead of b, I can write a 6 plus 2a. So now I'm going to have 10a plus 6 plus 2a equals -2. And now I just have an equation with a single unknown in it, just an a. So this would be 12a plus 6 equals -2. And so 12a is -8, so a would be -3/4. Is that right? Nope. -2/3. -8 over 12. Divide the top and bottom by 4, and you get -2/3. Okay, so there's my value for a. And then now that I have a value for a, I can go back to the equation I had b in terms of a, plug in -2/3, and we get b is 6 minus 4/3. So 6 is like 18 thirds minus 4 thirds is 14 thirds. So now I know what A is and I know what B is. I come back to my other equation that has A, B, and C in it, and I solve for C. So I've got negative 2 thirds plus 14 thirds plus C has to equal 4. So 12 thirds, which is 4. So C is 0. Okay, so we found the member of the family. It is the function that looks like ax squared plus bx plus c that has the values of a, b, and c that we just found. So it's going to be f of x equals negative 2 thirds x squared plus 14 thirds x plus 0. You don't actually have to write the plus 0 because it's the same thing with or without it. That's the member of the family that we were looking for. Yeah, so this guy had 3 parameters, so I needed 3 equations. And in order to get 3 equations, they have to give me 3 pieces of information. They gave me a point, that's 1 piece of information, and they gave me the slope at 2 different x values. So that's 2 more pieces of information. 3 parameters, you need 3 equations. And then you just solve them using your favorite technique from algebra. All right, let's do another one. Okay, so now I have a family of functions that if you did your reading for today, you read about it in the book. F of x equals e to the negative x minus a squared over b. And this function is related to a useful tool in statistics called the normal density function. I'm just going to analyze e to the negative x squared over b because that minus a in parentheses there is just going to represent a horizontal shift, if you remember from transformations from an algebra class. So I'm going to analyze it without the a and then just tell myself after, and that a represents a horizontal shift. So I'm going to assume b is positive throughout the analysis. So we need to be given that b is a positive number. And I want to find any local extrema as well as the concavity and the end behavior of this function so that I can try to like draw a picture of it, know what it looks like for different values of b. Okay, so if I start by finding its end behavior, that means I want to find the limit as x goes to infinity of e to the negative x squared over b. So what happens as x gets very large to this function? Yeah, e to that thing is going to get really, really small because it's e to a negative, right? And e to the negative x, you remember from a previous discussion that e to the negative x looks like that. And now we're going to square it, so it's going to go to 0 just even faster. Okay, and then what if I look at the limit as x approaches negative infinity? Yeah, but you're squaring it. When you plug in negatives into something that you square, it becomes positive. So this is exactly the same as what happened at positive infinity. All right, so we know the end behavior. Just label our work there, end behavior. All right, and then if I want to find local extrema, how do you find local extrema? Derivative. What do I do with it? You got it. Okay, so to find local extrema, first we find f prime of x. So what's the derivative of e to some stuff? E to the stuff, so it's going to be e to the negative x squared over b times the derivative, I'll just write this out, d dx of negative x squared over b. So f prime of x is e to the negative x squared over b times, what would the derivative of negative x squared over b be? Yep, negative 2x over b. You can think of that over b as a coefficient, because you could read that as negative 1 over b times x squared, and then just take the derivative of the x squared. The quotient rule would lead to the same thing. One of the terms of the quotient rule would drop out, because the derivative of b would be 0. Okay, so the next thing we do is we set that derivative equal to 0, and we solve. And this, once we solve, those are potential extrema, if you remember that. So I'll solve this thing to find any potential extreme values. I already have it factored. That's nice, because when you have a product of two things and the answer is 0, one of them has to be 0. So either e to the negative x squared over b equals 0, or negative 2x over b equals 0. E to the something, can that ever be 0? Nope, it's got a horizontal asymptote at 0, never gets there. So this never is true. And negative 2x over b, when is that 0? When x is 0. Okay. So we have one potential extreme value. We need to know if it's a max or a min. What do you think? How do you know it's a max? You graphed it. How about if you wanted to use your brain? Yeah, the end behavior is approaching 0. So x equals 0. Well, that doesn't really tell me if it's a max or a min, because it could be approaching 0 from below, right? So let's see, if I were to try to sketch what I know I've got an extreme value on the y-axis at x equals 0, and my graph approaches 0 in the end behavior, so it could look like this, right? But it could also look like this. We don't know. Both of those have an extreme value at 0 and approach 0 in the end behavior. So how do we figure out if we have a max or a min? You can take the next derivative and look at the concavity at that point. Oh, if we plug in 0 into the original function, we could see if it's positive or negative. Yeah, that would work also, if we knew that value. And so that's two ways. There's a third way, the sign chart, right? The first derivative test. I don't care which one. We're supposed to find the concavity anyway, so we have to take the second derivative anyway, so maybe we'll do that. So concavity f double prime of x. So here's my f prime, right, written as a product, which means that to take the second derivative, I will use the product rule. So I'll have first e to the negative x squared over b times the derivative of the second. The derivative of negative 2x over b would be negative 2 over b, plus the second, negative 2x over b, times the derivative of the first. The derivative of e to the negative x squared, I know what it is, right? It's e to the negative x squared times negative 2x over b. All right, so to find intervals of concavity, I set this thing equal to 0 and solve for x. But if I just want to test my local extrema, I take my x equals 0, plug it in here, and use the concavity to determine whether I have a max or a min, right? So let's see, what's f double prime of 0? So e to the 0 would be 1. Negative 2 over b, that doesn't change. Negative 2 over b times 0, that's 0. So it doesn't matter what the rest of this stuff is, it'll be 0. So I get negative 2 over b. Is that positive or negative? It's negative because they told us that b is always positive. So it's negative 2 over some positive number. It's negative. So f double prime of 0 is negative, which means that at 0 the function is concave up or down? Down. So if you have an extreme value and the function's concave down, that extreme value would have to be a maximum. Okay. So I now know that that's a max. Now to find intervals of concavity, I have to set this second derivative equal to 0 and solve it. And I'm out of room, so it's on a new page. Okay, equals 0. Have to try to solve this thing. Yeah, it's not nice. It's not nice. But there is an e to the negative x squared over b in both terms. I could factor it out. So I'll have e to the negative x squared over b times, and then I'm left with negative 2 over b plus 4x squared over b squared. I just multiplied the negative 2x over b times the negative 2x over b equals 0. E to the negative x squared. So, okay, so this is now written as the product of two things, right? Sure, I could. Yeah, I could factor out negative 2 over b. You want to do that? So I'll have negative 2 over b e to the negative x squared over b. So that actually leaves me now with 1 minus 2x squared over b. Yeah, because now distribute that negative 2 over b and you'd get positive 4x squared over b squared equals 0. Okay, so I have this written as the product of two things equaling 0. One of them has to be 0. So either negative 2 over b e to the negative x squared over b equals 0, or 1 minus 2x squared over b equals 0. This is an exponential, can never equal 0. And 1 minus 2x squared over b, I want to solve that thing for x. So I get 1 equals 2x squared over b. So b equals 2x squared. Divide both sides by 2. X squared equals b over 2, which means that x is plus or minus the square root of b over 2. So that is places, those are locations where my concavity changes. Okay, so I know that at 0 it's concave down. I have a max and it's concave down. And then somewhere to the right and somewhere to the left, it switches to concave up as the function approaches 0. So let's try to sketch all the things we know now. I know I have a maximum at 0, and I know that it is concave down because I did f double prime of 0 and it came out negative, so I know I'm concave down there. And then I know that at positive square root b over 2 and negative square root b over 2, the function switches concavity. So it's going to be concave up at those points. And I know that in the end behavior, we approach 0. So the function looks something like this. Concave down, 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 up, 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 up. Concave down until root b over 2, and then it switches to concave up as it approaches the end behavior. It's a terrible sketch, but I have a much better sketch over here. So in this case, I drew the function for b equals 1, sort of the easiest value for b. So if b equals 1, that means that my changes in concavity should be at plus or minus square root 1/2, right? Which is approximately, let's do it on a calculator, 0.707, I think. Yep, 0.707. So it does in fact have a maximum at 0, just like we predicted. And then it looks like it changes concavity where it's down, and then maybe like right here-ish, it switches to concave up. So everybody see the change in concavity from bending downwards to bending upwards. And that point right there looks like a point of inflection, and if I drop a perpendicular, that point is 0.707 approximately. And then we have another one on the other side. Concave down, switches to concave up, about right there. Negative 0.707. And then when you change the value of b, those points of concavity move. And I can use this little slider. And so the points of concavity change based on the value of b. Okay, so your group activity is to examine the surge function. Earlier this semester, we learned about surge functions. You did it as a group activity a ways back. They can be used to model the levels of drugs or medications in the bloodstream as a function of time since it was administered. So you get this surge, right? It goes up really fast, and then over time, it kind of decays away. So you're going to look at surge functions, the family of surge functions that look like that. So you've got 2 parameters, A and K, and you're going to investigate this family.